Welcome back to ECE 442-542. Homework number 3 is due, I guess it looks like a week. And a lot of that is dealing with inverse Z transforms, and hopefully we'll go over that today so that it will be fairly clean for you to work through, I hope. And just as a reminder, exam number 2 is after spring break. If you didn't know spring break was coming, you now know it by all the tents that are being set up on the mall. That happens for spring break purposes, and that's indicating that spring break is right around the corner. That's the Festival of Books. They have that underneath all these tents. There's also a couple of things that you'll refer to outside of class. One is the Region of Convergence resource. That's now included in Unit 3 on D2L, and there's some notes. There won't be a video with these notes, but there are some handwritten notes on how to approach performing inverse Z transforms when you have complex poles. And those notes are on D2L. Those notes will make more sense after today's discussion. That's the goal. The other goals, well, is to look at the inverse Z transform. We'll look at that via an example, but before we even do that, we're going to try to go back to where we are coming from, and that is, how did we do inverse Laplace transforms? We'll start there. That will hopefully transition us into how do we inverse Z transform. And we'll go back to this region of convergence and the different patterns with respect to the poles. When do we expect poles to correspond to causal, or if it's modified, a right-sided sequence? When do we expect poles relative to the region of convergence to correspond to anti-causal, or if modified, left-sided? And here I'm showing you why it could, or how it could be modified, the region of convergence. We remove these extreme locations or points, Z going to infinity. That includes a lot, meaning infinity can be anywhere, any direction. Z equals 0 is just a dot. And we could have two-sided behavior sequences based on what our poles look like relative to the region of convergence. And whether or not we have bounded and unbounded responses, that's going to be determined by whether or not this region of convergence includes the unit circle. If the region of convergence doesn't include the unit circle, then we have unbounded responses. If it does, if the region of convergence includes the unit circle, then we have bounded behavior, whether those sequences are right-sided, left-sided, or two-sided. That's one of the main points to take away from today. Then if we have time, we'll talk about where is this notion of a system being stable when all of its poles are inside the unit circle. We'll talk about that particular issue. And before exam 2, we want to more thoroughly examine this notion of discrete equivalence. If somebody gives you a G of S, how do we find its equivalent in the Z domain? And G of S could arise as a filter. It could arise as a system. It can arise for many different purposes, and how we perform that discrete equivalent depends on what we're starting with G of S. It may be preceded by a zero-order hold. It may not be, and that might influence how we make this discrete equivalent. So there's not just one way to go from G of S to G of Z, is what I'm trying to emphasize. Let's start with where we hopefully are familiar. So I'm saying recall or revisit or refresh our memory, and relative to the inverse Laplace transform. If we wanted to inverse Laplace transform this expression for capital X of S. We're in the S domain. It's the frequency domain, but now it corresponds to continuous time waveforms in the time domain. That transform is now 6 over the product, S plus 2 factor times an S plus 3 factor. And what have I done on the rightmost side of the equality? What's that called? Partial fractions. So I've now done a partial fraction expansion, and what we will talk about now is how to find C and D. But if we had C and D, what would X of t look like? What would the expression for X of t equal? If we knew C and D, or let's just assume that we have C and D as numbers, and we'll just call them C and D. If it's now C over S plus 2 plus D over S plus 3, what does that look like in the time domain when we inverse Laplace transform? Or, let me give you some more history or background. What do the 2 and 3 correspond to, or what good are they, or what are we interested in, or why are we even looking at S plus 2 and S plus 3? Or, a lot of ors. Well, there's water, so we have to paddle our way around. Sorry. What values of S cause the denominator to vanish? Those are the poles of this expression, capital X of S. And we know poles give us the natural behavior of this transform. So if that represented a system, if you walked up and kicked it, it would naturally want to move or shake with the modes corresponding to poles that are positioned at S equal to minus 2 and S equal to minus 3. And those modes are e to the minus 2t and e to the minus 3t. Those are our modes in our response, which I'm trying to now extract. I guess if we were on water, I'm now trying to fish and pull some fish out of the water with these answers. C times what? The mode associated with the pole at minus 2, or we now have C, e to the minus 2t, plus D, e to the minus 3t, t greater than or equal to 0. And we typically have dealt with the one-sided Laplace transform, meaning really only worried about right-sided time domain waveforms. That's why we could find a unique X of t when we were doing this inverse Laplace. We always were assuming a particular structure for its region of convergence. You may not have even talked about the region of convergence with Laplace transforms. But now let's talk about or remind ourselves how we found C and D. One method, when we have distinct poles, which we do here, we had a pole at minus 2 and a pole at minus 3, we could use the Heaviside cover-up method. What's that? Well, if you go back to this expression and you use your hand and you sort of cover up the S plus 2 factor on the left and then evaluate at the location S where S equals minus 2, then you'll find the expression or the value for C. Meaning C can be found by multiplying both sides by what's underneath C, which is this factor S plus 2, and setting that factor equal to 0 by letting S equal minus 2, which corresponds to now saying C is equal to 6 over S plus 3 when S is equal to minus 2, or C is in fact equal to 6. The same cover-up method can be used for D. We multiply all terms by this factor S plus 3, which was underneath D, evaluate it at S equal to minus 3, and we end up with D equaling minus 6. That's the cover-up method which is fairly straightforward and fairly powerful. It allows you to quickly find one equation and one unknown, and you don't have to worry about coupled equations to try to evaluate for C and D. But it may not be the most general, because here it's really assuming we have distinct poles. That's what makes this cover-up method powerful. But this is what we end up with now with the particular value for C and D, and we could write it two different ways. We could write it with this comma and say, oh, this is for non-negative time, or we could put a compact form together and use the switch. We could use this unit step as a switch, and we're saying this expression, 6e to the minus 2t minus 6e to the minus 3t, is only going to be active when u of t is switched on. U of t is switched on when the argument of that unit step is non-negative. And that means it's equivalent to the line just above it. Keep those, or that thinking, in mind as we move on. Anybody have a TI Inspire? You can now use that, or the TI-89. It does this partial fraction expansion for you with the expand command. And if you want it to look like this ratio of polynomials, you just hit Control Divide, and now it pops up into a division operation, and it looks a little cleaner. And if you actually captured your screen, it would look something like that. Expand 6 over s plus 2 times s plus 3, it immediately does the partial fraction expansion for you. Now, don't go out and buy that calculator necessarily unless you really want to do it, because you can do this cover-up method pretty quickly. But if you've already purchased that calculator, you might as well use its capabilities. But I'm not receiving any kickbacks on the calculator, so don't think that I'm marketing or advertising that. I'm just letting you know what you can do if you own one. There are other methods for finding C and D, and some of these other methods might actually produce coupled differential equations. You guys need to let me know when screens aren't on. Sometimes I'm not awake, but I think we now are all active. All eyes now are on screen. Sorry about that. But one of the approaches would be to just put them over a common denominator. You have 6 over s plus 2, s plus 3. You've done the partial fraction expansion into c over s plus 2 plus d over s plus 3. Put them back over a common denominator. You get this numerator on the right-hand side that's supposed to equal 6. Well, that means that the coefficient that scales s must be 0, or said another way, c plus d equals 0. And the constant coefficient, which is 3c plus 2d, better be 6. And now if you like to solve everything with linear algebra, you could put that into a matrix. You could say, oh, I now have c plus d equaling 0, and I have 3c plus 2d equaling 6. And now if you invert that 2 by 2 matrix, you better end up with c, d, that column, equaling what we calculated before, 6 and minus 6. But the cover-up method solved those in an uncoupled manner. If you don't like that, plug in some convenient values for s in this partial fraction expansion. And what is not convenient? Well, what's not convenient are picking those s values that are the same as your poles. Then you have infinity equals infinity, and that doesn't tell you anything. Stay away from pole values for convenient values of s, so don't let s equal minus 2 or s equal minus 3. Let's say s is equal to 0. That tells us then that 6 must equal 3c plus 2d. That looks familiar. And at s equal to minus 1, we get 6 is equal to 2c plus d, and you have to make sure that the denominators were consistent in order to compare or equate the numerators. But now if you put those into two equations and two unknowns, you better end up with c and d equaling what we already have found. Questions on your memory? Everybody now back to wherever you learned Laplace transforms, that classroom, that chair, or maybe that space, wherever it was that you were playing with Laplace transforms, maybe in the library. Nobody goes to the library anymore, do they? Just for class, huh? When there was a class in the library. Okay, so you didn't go to the library, but anyway, somewhere where you learned Laplace transforms. Maybe now you're back there. Now when somebody says Z transforms, you're back here in this classroom thinking about, time sequences in discrete time. So let's look at what we can do if somebody now gives us a capital F of Z of this form and says, what's little f of n? And we know, or hopefully we will know after today, that we also have to have the region of convergence in order to find a unique little f of n. I could come up with different structures for f of n. Well, the structure I'm going to say is the same, but different behavior or different values of little n being associated with different modes depending on the region of convergence. In general, what's the structure of f of n for this example? Can you write down the structure for f of n without identifying coefficients other than the modes? And here I would argue that the structure in discrete time is more straightforward than the structure in continuous time. What's the structure of f of n? If I now said, oh, you're out of time, but turn in your exam, you go, well, let me write down the structure. You should be able to do that in like 10 seconds. The length of time that it takes you to fill in that line. What does the structure look like? What are the modes? They're equal to the poles, aren't they? They're the values of z that cause that denominator of f of z to vanish. I have one at 1/2, and I have another one at 3/4. And those are going to evolve within. And I could say, oh, I don't know the weighting, so let me just call those alpha 1 and alpha 2. For what values of n is this structure going to exist? Do we know? Can we determine? What if we now said, oh, let's just, I don't remember, but I can draw the z-plane. So you start drawing. And we now have two poles, one at 1/2 and one at 3/4. And where was our region of convergence? It's outside the biggest pole. Our region of convergence now, that's a circle of radius 3/4, and here is our region of convergence. It's outside of that largest pole. Does that now tell us anything or provide any insight into when we know this n is valid, little n. Now n needs to be non-negative, doesn't it? Because we now have a causal sequence since all the poles are interior to the region of convergence. So this region of convergence now allows us to say that n is greater than or equal to 0. What can we say about the behavior in terms of bounded or unbounded behavior for f of n? Is the f of n bounded or is it unbounded? F of n is bounded, and how did you arrive at that conclusion? You've now said that f of n is bounded. Could you have determined that by simply looking at plugging in non-negative values for n and seeing that these are collapsing? 1/2, 1/4, 1/8, 3/4, 9/16. Those are all shrinking. They're converging. You could have just looked at f of n and said, oh, f of n is bounded. Or you could have said, which I think I overheard, was the region of convergence includes the unit circle. Meaning, if we now sketched the unit circle, if we put that into our z-plane sketch, do you see that it now is included in the region of convergence? And because of that, our sequence in the n space, in the time domain, is bounded. Whenever that unit circle is included in the region of convergence, we know that our behavior is bounded. Now, if we wanted to find how to do inverse Z transforms, and we were trying to argue based on what we've learned from the Laplace transform, how did you do inverse Laplace transforms in different classes? Did you derive them? Did every time you saw a transform expression, you went and re-derived each Laplace transform pair? I'm guessing not. You probably worked with a table, didn't you? If that's the case, if we now have Z transforms in a table, what entry would we be looking at to try to find the inverse Z transform associated with this structure for little f of n? I better not write in red. People won't, they'll if I now had alpha r to the n, what would that look like in the Z domain? This is now in the time domain, or n. Now what's in the Z column in my table associated with this entry, alpha capital R to the n? What would its Z transform look like? What's the denominator? We said the denominator is such that if we have a pole, then that gives us our mode, R. That denominator then needs to vanish when Z is equal to R. And if we're now writing this in terms of positive powers of Z, we would actually have a Z in the numerator, and we would scale it by the same factor alpha. Okay, so this is now what we would expect to see in our Z transform table. Suppose that we did a direct partial fraction expansion on capital F of Z. Let's say now that we're going to go ahead and be performing a direct partial fraction expansion on x of z. Well, it wasn't x of z, was it? It was f of z. I'm still trying to warm up from the walk over. All right, so performing a direct partial fraction expansion on f of z, if we did that, f of z was now this z over z minus 1/2, z minus 3/4. What would the partial fraction expansion look like? Structurally, it doesn't look any different really than what we had for the Laplace. What was how many terms do you expect to see in the partial fraction expansion? 2, because we have 2 poles. What's in the denominator of each of those terms? What's in the numerator? Some coefficient and another coefficient. Now, what's concerning is the following. Does this structure look like this? Do those have the same structure? In the bottom, is the bottom missing something? Now I feel like we're at Sesame Street. One of these things doesn't belong, or one of these things is not there. Is the numerator the same? No, one's alpha and one's a. Okay, let's look beyond the Greek and the alpha. But the other's missing a polynomial, isn't it? Z. So we can't, this is inconsistent. So we can't just do a direct partial fraction expansion on our z transform expression, capital F of z. We have to sort of go a little bit, do a little bit of forethought. And what we can do, so we want to end up eventually with a term like is alpha z over z minus r in our partial fraction expansion. Well, we can force that z to appear in the numerator if we factored it out to begin with. Meaning, instead of doing a partial fraction expansion directly, let's instead work with the partial fraction expansion of f of z over z. In our particular case, it's going to be fairly convenient because we had a z sitting up there in the numerator. But really what we're going to do now is we're going to say, oh, let's just do that. Let's partial fraction expansion f of z over z, and those z's cancel. That's what I want to do. I'm going to erase this because people will go, where'd that come from? When they start looking at the notes, since half the class will be looking at the notes. That wasn't funny. Well, I guess I allow it, so that's fine. Actually, a third of the class is online, so I can't argue with them, right? It's just this classroom is a little bit bigger than we need. Other than on exam days, then it's about right. All right, so let's look at doing the partial fraction expansion of f of z over z. Now we have 1 over z minus 1/2, z minus 3/4, and that, let me just go ahead and call these something different so that you don't confuse it with what we had before. Let me say that coefficient upstairs is a bar, and here is b bar on top of the factor z minus 3/4. Now we can solve for a bar and b bar using 1 over z minus 1/2, z minus 3/4. You could even use your calculator to do that if you wanted to with the expand and solve for a bar and b bar. But then when we want to find f of z, we multiply both sides through by z, and we now have f of z equaling a bar z over z minus 1/2 plus b bar z over z minus 3/4. Are you following what I'm trying to communicate? We have to modify f of z by dividing by z in order to do the partial fraction expansion in the way that we've learned it using Laplace transforms, and then we're on familiar turf. We can do it just like we did Laplace transforms. Now we have the coefficients, a bar and b bar, boom. Now we have an expansion or a factored version of f of z that contains in this right-hand side terms that I can find or locate in the table, in the z transform table. And once I have those pairs identified, I now know that little f of n is in fact a bar 1/2 to the n plus b bar 3/4 to the n. And because I knew my region of convergence was outside the largest pole, I know I had a causal sequence. I now know when or for what values of n this sequence is defined. Just for grins, you could actually go back and look at this and use the cover-up method to solve for a bar and b bar. If we did that, a bar would be what, formula-wise? We multiply all terms by what's underneath a bar, z minus 1/2, and evaluate the left side at z equal to 1/2. Or a bar becomes 1 over z minus 3/4, evaluated at z equal to 1/2. Or that now becomes minus 4. B bar the left-hand side just ends up, when we cover up the z minus 3/4 factor, we're left with z minus 1/2. We evaluate that where that factor z minus 3/4 vanished, which is when z is equal to 3/4. Now we have 1/4 downstairs, which ends up being 4. And we now have f of n equaling minus 4 times 1/2 to the n plus 4 3/4 to the n greater than or equal to 0. And what if somebody says, why? Can you now explain why you're putting this range of n, or making this a causal waveform? Can you explain to somebody why we were able to conclude n was greater than or equal to 0. Everybody have an explanation for that? Yes? No? What do you remember? Do you remember the definition of the Z-transform? Can you fall back on the basics? So let's remember the definition. Of the Z-transform, which is f of z is this summation from n equal, and in this case we can just say in general, it's from minus infinity to infinity, f of n, z to the minus n, which the series expansion produces f of minus 2, z to the 2, plus f of minus 1, z to the 1, plus f of 0, plus f of 1, z to the minus 1, plus f of 2, z to the minus 2. And why am I trying to remember the Z-transform definition? What does that help us with? Well, now we want to combine that with the knowledge of our region of convergence. Here's the Z-plane. Our region of convergence was determined, or it was given to us, to be beyond our largest pole, and now we could pick any point z in that region of convergence and plug it into this series expansion, and that series expansion needs to be bounded for that particular z value. If we now say, oh, here's a z, but somebody gets a little bit cute and says, well, let's just let that go off to infinity. If you plug that in here or in here, what does that imply about the coefficients that are scaling z, z squared, z cubed, if z is allowed to go off to infinity, and we want that right-hand side to be bounded? We're forcing all of those negative argumented coefficients to be 0. This is now saying that this piece needs to be 0, this term needs to be 0, as do all of those pieces. That's why we could say that n was greater than or equal to 0. That's the justification, and you need to remember that for the final, or exam 2, or exam 3. Everything from this point forward. From this point forward, I now remember. Repeat after me. No, we won't have that ceremony, but we basically just did. You now have learned why that's causal relative to that region of convergence. And you could have quickly found that partial fraction expansion if you went into your calculator and said, oh, let me just punch in expand, and now I have 1 over z minus 1/2 times z minus 3/4, and it will now produce 4 over z minus 0.75 minus 4 over z minus 0.5. And now you have your result fairly quickly in terms of how to take that back into the time domain. That was for a region of case number 1 in our different region of convergences, which corresponded to a causal waveform. And I think you know where I'm going now. It's a little after 6. It's dinner time. So now we have to talk about another region of convergence, which looks more food-like, a donut, right? Wrong time of day for a donut, but just shift 12 hours. We're good at shifting. So now what about, I guess if you're playing along at home, you're probably watching this at breakfast. So maybe it's appropriate. What about an annular or donut-shaped region of convergence? Meaning, what if you were now given the following: a pole at 1/2 and another pole at 3, and in fact the region of convergence now is bounded by those poles. In this particular picture, this is our z-plane. We now have a region of convergence such that the magnitude of z is less than 3 and bigger than 1/2. That's our region of convergence. It's annular. Not knowing anything more than this picture, can you tell me anything about the behavior of the sequence in the time domain corresponding to this particular picture? Can you say anything about the bounded nature? Is it bounded or is it unbounded? The sequence corresponding to this frequency domain picture. Yes. Did everybody hear that? Probably not at home, did you? It's bounded because, and the justification was, our unit circle, if we drew it somewhere in here, the region of convergence includes the unit circle. And because of that, now we know that whatever the sequence is, it's bounded. We have a bounded time domain sequence. Let's go a step further. Suppose I said, what's the structure? And for purposes of just giving it a name, let me say that this is capital F of n again, and I want you to give me the structure of little f of n associated with this picture. Everybody have the picture? They're locked into that. So what's the structure for f of n? And if you just wanted partial credit, what's the first pieces to try to get partial credit for the structure of f of n? What could you use to get partial credit? If I say structure, what are you now putting on your reading glasses and trying to find in this picture? Where are the poles? Wherever they're located, those locations produce the structure. That's how this system will naturally move if it's excited or kicked. So now we know that the structure has 1/2 to the n and 3 to the n. And we could say, oh, this one's weighted. Let me move this a little bit. So I'm going to move this over. This one's weighted by alpha 1. I'm going to move this one over too. My paper's not that wide, although it's infinitely wide, isn't it? What do we know about f of n? Look in the upper left-hand corner of the screen. We know it's bounded. If we know it's bounded, that tells us exactly when we need to turn these different modes on and off. 1/2 to the n, what values of n does it need to be turned on for? Because we know this is bounded. When is this need to be turned on? This is for non-negative values of n. And we can make that happen by saying, oh, let's just switch it on with a u of n. What about the second term in f of n? If it's to remain bounded and it's some number smaller than, whoops, I'm still in the freezer. Wasn't it a 3? I was just checking if you guys were awake. Apparently you're not that aggressive with your comments today. You let me just revert back to an earlier example, and I'd switched it. I'd put the poles at 2 different locations to give me a bigger donut, right? And a donut that included the unit circle. If I'd kept it at 3/4, I wouldn't have had the unit circle. And I wanted things to be bounded, right? All right. So what values of n is this true for? Do you see how I caught my error? I knew I needed to be bounded for negative n's, and 3/4 was not going to work. And I'm going, what in the world am I doing? You have to think on your feet sometimes here. And we're in a collaborative learning space, so you guys are supposed to be thinking all the time, collaborating and learning in this space. Right? Maybe that's why half of you didn't show up. Huh? You like to just play along at home. Where's this? N less than 0, and we can make that happen with u of minus n minus 1. So let's verify that in fact this is indeed true or consistent with what this thought process was that we've just laid out. Suppose now we're given the following. We're given f of n is equal to f1 of n, which let's say it's now 2, 3 to the n for n negative, and it's f sub 2 of n equaling 4 times 1/2 to the n for n non-negative. And now we could pretend that this is a final exam problem, and we say, okay, find f of z. And we could also note, if we wanted to, what do we know about the poles and the region of convergence? What's their relationship? If we end up with an answer, where do you expect the poles to be in that answer? Based on this structure for little f of n. Can you anticipate where you want the poles to be? After doing all these steps in the Z transform, we should be able to sort of know what part of the answer in the back of the book is. Where are the poles going to be? They're determined by the modes, and the modes are at 3 1/2 in this expression. So, and we also know that the poles relative to the region of convergence, how are they related? Are the poles included in the region of convergence? I see some heads going left and right, and I see some heads going up and down. Which way should our heads be going? Should the region of convergence include poles? No. The poles bound our region of convergence, so the poles are not in the region of convergence. So if we get an answer and it's inconsistent with this fact, then we need to go back and check some things. So now let's rewrite f of n. Instead of 2 lines, let's write it in 1 line. Suppose I now say f sub 1 of n. What do I need to switch it with? f1 of n was on when n was less than 0. The switch I need for that, I need the argument to be non-negative when n is negative, and that will be minus n minus 1. F sub 2 of n will be switched on with a standard unit step. Now I've written f of n in 1 line, if that was helpful. And we can now say that f of z, we can compute these since the Z transform is a linear operation. We can now compute the Z transform of little f1 of n and the Z transform of little f2 of n and combine those to find capital F of z. Or let's now look at f1 of z. The Z transform of little f sub 1 of n. That's this sum from n equal minus infinity to infinity of 2 times 3 to the n z to the whoops, let me go ahead and put the switch in there to allow me to figure out what my limits on my sum are going to be. This is now a switch that is on when minus n minus 1 is greater than or equal to 0. Right? When its argument is greater than or when it's now negative, or if we add n to both sides, when n is less than or equal to minus 1. Or when n is less than 0. So that's what we want. Now let's continue. Now we can remove half of that, the terms in this infinite sum that has 2 infinities, 1 to minus and 1 to plus. We just need to keep the negative ones. And let's factor out the 2. We now have 2 times this sum from n equal minus infinity up to minus 1 of 3 to the n z to the minus n. Or I could combine that by just raising it to the power n by putting the z downstairs, and so I now have 3 over z to the n. We okay with that? Let's now not worry about that 2 for the time being and just try to find what this encircled expression equals. Let me call that S. S is now 3 over z to the minus 1 plus 3 over z to the minus 2 plus 3 over z to the minus 3, etc., all the way to minus infinity. When is that tail going to behave? Now I have something that I'm inverting and summing. And that something is in the basement of this sum. So I have 1 over 3 over z. I have plus 1 over 3 over z squared, plus 1 over 3 over z cubed. What do I need 3 over z to be in order for that sum to be well behaved? Or to be, for s to be bounded, or to be a finite value? I'm doing this a little differently than we've done before, just hoping that maybe one of these ways of doing it you like, and that's what you'll stick with. In this case, what do we want to know or have happen for the magnitude of 3 over z? That's our common ratio in all of these terms. And it's downstairs, and we keep raising that downstairs piece to higher and higher powers. 1 over that common ratio, 1 over that. What do we need that ratio to be, size-wise? Have this geometric series, and it will be well behaved as long as that common ratio is greater than 1, right? Because it's downstairs. And now we can solve that for the magnitude of z and see that, oh, z needs to be less than 3 in magnitude for this s to be a finite value. What is that s? Well, if we multiply both sides by that common ratio of 3 over z, then the first term is actually going to be 1. The next term, which is 3 over z to the minus 2 times 3 over z, is actually 3 over z to the minus 1. And we now pick up that infinite tail in this new expression. If we compare the black and the blue, it's all beat up. It's black and blue. Sorry. If we subtract the bottom from the top, we end up with 1 minus 3 over z s equaling minus 1. And pay attention to that minus 1. That minus 1 is there because we now had summed over negative values of n. Or this now says that s is equal to minus 1 over 1 minus 3 over z. Or you might see somebody write that as minus 1 over 1 minus 3 z to the minus 1. Or if we multiply both top and bottom by z, which is 1, which is allowed, it's minus z over z minus 3. And when is that bounded? S is bounded when, or we could say f sub 1 of z exists when this common ratio 3 over z magnitude was bigger than 1, or when z is less than 3. Now we have the first piece. We have f sub 1 of z is in fact equal to, well, it was partly made up of s, but it was scaled by 2, wasn't it? We didn't incorporate 2 into s before. We just kept that to the side. F sub 1 of z is now 2s, or it's now 2, which was minus z over z minus 3, and that was true as long as the magnitude of z was less than 3. This is what we had then. Here's ROC part 1 for f sub 1. This was a time sequence when n was less than 0, or anti-causal. What about the other piece of capital F of z? F sub 2 of z. That's this 4 times summation from n equal, I'm going to do some shortcuts. I'm going to just do the causal piece. N equals 0 to infinity, 1/2 to the n, z to the minus n. And when is that going to be a finite value? What's the common ratio? What would be scaled by n, or the power n in each term? It's 1 over 2z. We want that magnitude now. Since n is positive, we need that common ratio to be less than 0. Less than 1. Have to stay awake. And this now says that 1/2 is the lower bound on z. The magnitude of z is bigger than 1/2. And without going through all the steps, we can simply say that f sub 2 of z is 4 times 1 over 1 minus 1 over 2z, and you can go through the steps if you want, or that's now 4 times 1 over 1 minus 1/2 z to the minus 1, writing it another way that you might see it in a table. Or we could multiply by 1, which is z over z, and we have z over z minus 1/2. And that's true as long as z is bigger in magnitude than 1/2. Or now we have a region of convergence number 2. Here's 1/2. Our z to be in the region of convergence needs to be outside of that boundary of inner disk size 1/2. And this is now ROC2. F, the actual z transform that we wanted, is a combination of 2 pieces, and we have to combine or find their common region of convergence, or the intersection of these 2 regions. The region of convergence for f of z is equal to ROC1 intersection with ROC2. ROC1 said that the magnitude of z was less than 3. ROC2 said that the magnitude of z is bigger than 1/2. And now we can see why we had that annular region to begin with. We needed the region of convergence to not include any poles, and our poles were at 3 and 1/2. We needed our region of convergence to be beyond 1/2 and less than 3. And there is now our region of convergence for f of z, and we can start making another useful interpretation, and that is that the unit circle is included in the region of convergence. Which allows that particular fact allows you to quickly answer, is f of n bounded? Because of the region of convergence including the unit circle, we know that the answer is yes to that question. What else do we know about f of n? How many tails did it have? 2. It was two-sided, wasn't it? And it still was bounded. The positive side was bounded and the negative side was bounded. And it's because of this annular region of convergence including the unit circle. What if we did another region of convergence for those same two poles? Suppose we did the following. Here's our z-plane, and now here's 1/2, and here's 3, and suppose our region of convergence is that a valid region of convergence? And what do I mean by that? What determines whether or not that's a valid region of convergence or not? What would invalidate it relative to the drawing or the picture? If we had any pole that was included in our region of convergence, it wouldn't be a valid picture. But this is valid. All the poles are not in our region of convergence. So this is now another region of convergence. For the same poles. I now am going to call that W of n in the time domain. What's its structure? We know it has those modes. And if I just ask for the structure, I'm not asking you to find alpha 1 and alpha 2. Do we know what values of n this structure is defined for? If you don't, you draw out or you write down the z transform expression and you look at what values of z would cause that expression to be bounded. Good question. Hopefully you didn't hear that at home. But the question was, why is that 3/4 and not 3? Because it's after 6 and I haven't had a donut, right? So the blood sugar is kind of bad, but it's now 3. Because we have a pole at 1/2 and we have a pole at 3. Thank you for the correction. That's now the mode We have modes corresponding to our poles, which one mode is at 1/2 and one mode is at 3. Now are we better? You are. Maybe not so much for me, huh? But when is this defined? When is this expression valid? For what values of n? Is it two-sided? It's not annular, is it, the region of convergence? So now you can flip a coin. And which way do you really want to flip it? Positive or negative for n? Write out your z transform expression and look at what values of z. Look at an extreme value of z, z going off to infinity. Oh, that annihilates or means that my negative n's have to be 0. I now know that this is true for n greater than or equal to 0. Now that we know that, can we answer this question? And it's a good thing you corrected my mistake so that we are consistent on this answer. Is W of n bounded? No, you just have to start raising 3 to higher powers. The answer is no. W of n goes unbounded as n goes to infinity. Or what can we say about the unit circle relative to this region of convergence? Does the region of convergence include the unit circle? No. And that's what then is another way of answering this. Or the unit circle is not included in the region of convergence. I'm hoping that you're becoming experts with region of convergence. Suppose that I now have a generic annular region. Meaning, here's the picture. I have some poles here, and let's say that my region of convergence is going to be beyond those, and these are all supposed to be circles, so you can draw yours a little bit better than that if you want. Here's another one, here's another one, and here's another one. Let me call this pole 1, pole 2, and pole 5, and this is now pole 3 and pole 4. And my generic annular region relative to those poles looks like that. What can we say about the modes associated with these 5 poles relative to this region of convergence? And how do we associate which poles with what kind of behavior? If I associate the poles I don't know how to say this, larger than or beyond the annular region, those are poles 1, 2, and 5. What values of n do I associate with those? They're beyond the region of convergence. or they lie outside the region of convergence. In our previous example, those were the anti-causal poles or modes. Or we could say the ROC is interior to poles 1, 2, and 5. And the poles smaller than or interior to the annular region. Bless you. And those were poles 3 and 4. Those are associated with n greater than or equal to 0. What else could we say about this generic annular region, or could we? If somebody now pinned the unit circle on this z-plane, we could tell something about the behavior, the bounded qualities or characteristics of those different poles. And I'll finish that up after. But if the unit circle was included in this region of convergence, even though we have all these different poles splattered around, what could you say about the bounded behavior of the sequence in time? It would be bounded if the unit circle is included in that region of convergence. We'll pick up somewhere close to that the next time we're together.